Hey, welcome back to another data-driven decisions. This is just a live stream. No one's supposed to be on here, but figured I would just live stream it. Check in, and the sound sounds good. We have video. We are live. Cool. All right, so we're in our next week of data-driven decisions. We had an awesome discussion about like editing and technical writing on Monday, since you've had a chance to look at both, getting started, both this first activity about looking at generative AI for like building instructions. And the reason I chose like toothbrushing is like, that's one of the first technical writing assignments that I got. Was I didn't use AI to generate toothbrushing instructions. Hard to say, but it's a great way to kind of test, like, am I getting my point across, and is it difficult to say this? Like it ends up being harder to get things across than you think. And on Monday, yesterday, we were taking a look at thinking about Monte Carlo, like what is Monte Carlo? So a little bit of this was learning, like, how does Monte Carlo get applied to different disciplines? And then how do you justify using it? So yeah, that was the main thing there. Looking at like our calendar going forward, the next thing coming up is this homework number 2, which will be due next week. So when we meet on Monday, we won't have anything new due. So and I did that so that you have a chance to go back and look at the improvements that I suggested for homework 0 and homework 1. And the main thing here is getting some practice looking at, like, how do I be specific and measurable in my technical writing? And I wanted to go through like a quick example, and maybe even dive like a little deep, try to dive deeper into what we're doing here today. So, and then the other thing that we're working on is that there are a couple readings. So if you go to this reading discussion, there's like a place where you can add questions here. So we have a couple of questions already, but this tech writing and AI is connected to those first 2 assignments for homework 0 and homework 1. And then also this technical writing audience. So when you're doing technical writing, like how do you choose the audience? And let's see, audience analysis. So types of audiences. So there's experts, technicians, execs, non-specialists. Then you want to adapt the writing. So you're trying to like add information that is needed for your readers. So in the case of our generative AI for Monte Carlo research, if you are a manager talking to other managers, then probably the thing that you're most concerned about is like, how many man hours is this going to cost, and how much money will we save? If you're kind of a lead engineer talking to managers, you probably have a lot of you're like putting forth technical knowledge of like trying to convey that if I can create this and have this work, then we will save money, because in the past my experience has shown is that the more we understand this problem, the more money we can get. But yeah, a lot of times, at least for businesses, the main thing comes back to money. So as engineers, we like to talk about like forces, energies, temperatures, and all these kind of things, but we have to translate that into like, what is the cost? Like if we're using an extra 3 joules each day, how much money is that? Like, is that a lot of money, or is that a little money? And so we can figure that out, right? So 1 joule in kilowatt hours. So 1 joule is 2 times 10 to the negative 7 kilowatt hours. And the reason that I do that is like price of a kilowatt hour. And here, no matter where we go, we end up with AI generated things, but on the low end, it's 6 cents. On the high end, maybe $1. So if you're talking 3 joules, it's nothing. There's no increase in cost, like at least per day. So now even we would need at least 1,000 days, right, to even start to talk about how it's costing $1 or $2. So just order of magnitude stuff. If we're talking like 5,000 joules, like now we're starting to say like, all right, well that's going to be times 60, so 0.6 of a cent per day, maybe that's a little bit more in line with what we're talking. All right, but let's come back to this assignment and maybe dive a little deeper into this. So I keep running out of tokens in ChatGPT. So I'm gonna try Copilot for Microsoft. Since we switched over to Microsoft, they have their own kind of version of ChatGPT. It's a little more closed. Like, let's see. Do we have? Yeah, we have no access to settings in here. But you know, it is an AI. So let's see how it goes. And let's see. I'm going to be a lead engineer. So I'm going to copy this over. I need you, let's zoom in so we can, to play the role of lead engineer at, and I love bike companies, so, well, I love bikes in general, so I'm going to do bike company, at a bicycle company. Justify the use of Monte Carlo methods in your role to design your bike product. And then I want to look at quantifying uncertainty. Let's do this. Quantifying and modeling process. Highlight the role of Monte Carlo in quantifying uncertainty in design and modeling process times. And for process, yeah, we'll start there. So let's see. So it's searching the web, so maybe it'll give us some useful information. All right, so it links us to a Wikipedia article about the Monte Carlo method. And I'm going to zoom out a little bit just to get a sense of load and stress, manufacturing processes, supply chain management. So I'm just trying to get an overview of what's going on, and risk assess. So this is telling me that I can assess risks, optimize based on variability in design. So one thing that kind of bothers me is about AI generated writing, and I can and most people, they can see AI generated writing when they know it when they see it. They can't put a finger on why. But one thing about it is that AI tries to mix up the vocabulary, but in technical writing, you want to keep vocabulary very consistent. So here it's using variations to describe like material properties, and then various loads. Like instead of saying like variations in load, like I want the same thing. Like if I want to talk about variations, then it's variations. And how am I defining that? Is it a standard deviation? Does each property have its own distribution? Like is one a Poisson distribution, one's a normal distribution, something else is a Weibull distribution? Like there's all these different ways of describing variation. So to keep changing the vocab from variations to various to different, like these are all synonyms, but we're trying to create a technical document that is easy to read, and it's already hard to read a technical document. It's even harder when we keep changing the words that we use as we're talking about it. So anyway, so then like one thing that I'm interested in here that I didn't mention in my prompt, but I was kind of interested to see if it would bring it up, was this supply chain management. So variability in supply chain processes, apply Monte Carlo methods, different supply chain scenarios. That's an interesting kind of rabbit hole to jump down. So let's see this. Can you show me a Python script for supply chain management variability in supply chain processes for lead times, raw materials, and components? Because that's what it said Monte Carlo methods could do. So show me a Python script. Create a Python script. So it's trying to create something. Let's see what it comes up with. And it takes a second. Oh, cool. Oh, and it ran the code for us. All right, so let's zoom out. And we'll come back up. Simulate variability in supply chain processes. So we're creating 1,000 simulations. We're going to define, it looks like we're going to be using normal distributions to say that like lead time for, I don't know what that means, but so there's a lead time, there's a raw material lead time, and then there's a component lead time. So each of these changes, like 10 plus or minus 2 days, 15 plus or minus 3 days, 20 plus or minus 4 days. And now we're going to take all three of those times. So we'll generate 1,000 different simulations. So as if we put in an order. So I'm putting in an order and they say it's going to take 10 days. Sometimes it takes 8, sometimes it takes 6. There's a really small chance that it'll take 4 days, but there's also an equal chance that it could take 16 days. So that's going to take, let's say, 10 days on average. This one is going to take 15 days on average. And then this one is going to take 20 days on average. So whenever I say buy me a bike for this supply chain thing, my expectation is that 10 plus 15 plus 20 is now going to be 45 days. So let's come down here, and sure enough, my mean, the most likely time for this scenario is 45 days. And that makes sense. But there's some times when we get it in like just a few times when we ended up with like 20 days, like really small. And there's just a few times that we ended up with at least 60 days. And that happened more often than the kind of 20 days down here. So this is kind of cool. And plus or minus standard deviation of 5 days. Does that sound right? That doesn't sound right to me, at least. The mean total. So total supply chain is the sum of those three. I would think it would be the sum of the square root of the sum of the squares of the standard deviations. So 2 squared, 3 squared, 4 squared. 4 plus 9 plus 16. I mean, but it is just taking the standard deviation of that value. But looking at a propagation of error, I think it's the square root of the sum of the squares of these three. Pretty sure. But anyway, so it spreads it out. And now I have like a concrete example of like how I can supply this, how I can talk about like total supply chain time design. So if I come back up to here, let's copy this one. And take into account that we can model supply chain times and supply chain times for thousands of scenarios and how that will save us money. So let's see if it fixes anything in this process, right? So costly rework and delays. So again, we kind of touched on this on Monday about like it's saying things, but it's not necessarily saying helpful things. And as engineers, it's better to say something that might be a little bit wrong. Like there's always some error in our calculations. Like this model, this like prediction that we just created is 100% error. Nothing about this is true because I don't know anything about the lead time. I don't know anything about these raw material. Like none of these predictions are true. So it's a complete like shot in the dark at this point. But I could do a little bit of research and change these values. Like I could look up lead time for like what is the lead time for aluminum for building like bike frames.